be nice if those who have questions would actually sit closer to James here. Okay. All right, so let's start it. So again, this session is about, Knuth does this kind of talks a couple of times. I witnessed 2 of these already. So it works like you could ask questions to computer science, of course also sad, but in principle you could say to ask questions to anything also outside of computer science and things where you think like Knuth has some interesting thing. So it's your floor now. So what's the question? Okay. Well, I said like please close to the questions at the right.
The algorithms you presented today, how easy is it to parallelize it, or parallelize them to accelerate the solution process?
Yeah, okay, well that's an interesting question. By the way, I wanted to say quickly in preface that I understand this room is usually used for final examinations. And so here I am, it's my examination day. When I was, before I retired, I already had the last day of class was so students could ask any question they wanted to. They wouldn't have to come that day, but if they wanted to, they were paying for the class and they had some question they hadn't answered, then they could come. I would answer whatever question they had. But I always said they could ask questions on any subject except religion, politics, or the final exam. But today you can ask questions on religion or politics or whatever, but I would encourage you to keep it questions for which my answers might actually make sense. In a way, a question about parallelism is almost in that senseless category because I started to work on our computer programming in 1962, and I promised, I said a table of contents at that time, it didn't include parallelism, and so one of the few chances I have that I don't have to read all the literature is when I see an article about parallelism, I can always turn the page because I never promised to write about it. I believe I believe that's really the future and extremely important. But my own expertise is in serial help. On the other hand, the algorithms that I showed today are really, in many ways, are about as simple to parallelize as anything, because you have a satisfiability problem and you can easily parse that up into problems that don't need any communication at all between the processes. And so the communication complexity is usually what kills things. Now, that's not quite true with the cause learning methods that that's the very last method. Because when one process learns a clause, then the other processes can use that information. But the other 5 algorithms I showed you, they were all they all partition the space in which you're searching into parts that they could each work on. And so in fact, Armin and some co-workers have something they call cube and conquer, where they divide these moving space up into several million subcubes. And they figure out that each of these subcubes can be handled in a few seconds, usually. And so then they distribute this among processors, and sometimes it will take 10 seconds, and sometimes it will take half a second, but it's easily continue to just keep the processor fed with things to do. And so last night when he resolved one of the problems that I gave him, he had, I think it was 24 processors working on it, and at the end the total time was something like it showed that somehow he was getting the effect is if you had 19 processors working full time on it, so you weren't getting 24 times speed, but you were getting very good speed. So this set is one of the cases that looks really nice on it. But also, there are other aspects of parallelism that I know just a little bit about which affects cache behavior. So a lot of the data structures that we use in combinatorial algorithms involve pointer data where we're jumping around in memory and we almost always get cache missed. But with multi-threaded computers, you can actually set one of your threads to go ahead and figure out what's going to be needed in the cache later, and that's another nice aspect of parallelism. That means we can resurrect some of the algorithms that we're not working with so well with cache hits. Sequential methods use a lot more memory accesses, but memory accesses are cheaper if the data is already present in the code. And so the methods based on linked data have a new life now because we can have different threads setting up the cache into prefetching operation. Thanks for the question.
Next question, so they can use this
one. Hi. So my question would be, if you visited a lot of topics while writing your books, do you have any topics that was your favorite or that you would like to revisit?
I'm sorry, I don't. Can you repeat?
Okay. Of all the topics that you visited while writing your books, which one was your favorite, or which one would you like to revisit?
Okay, so there are too many questions of this kind of thing. Which are my favorite or top 10? So, I mean, it's like asking a parent which of their children is better. So you like whatever I'm working on, I always consider it as the most exciting in the world. But then I like different things in different ways. So I could just go through each part and I would say, this is the aspect of it that was fun for me. But more generally, I don't know. I found that early on, I found that I was able to entertain myself. I didn't need somebody else to be feeding me stuff, but in a situation I found myself in, I wasn't bored because I could think of something interesting about, and so I think that's one of the keys of life is to learn how to ask interesting questions about whatever you're faced with. Instead of saying, instead of viewing the world as something where somebody else is supposed to entertain you, view it as something where if you are bored at a particular moment, you say it's because it's your fault that you haven't found what's interesting about the situation, instead of that it's somebody else's fault for not making it interesting for you. But I've always, when I'm studying stuff in college, I used to find the first chapter really was so interesting I could hardly ever get into the second chapter. I knew mathematics and they introduced the absolute value function. I hadn't heard about the absolute value function. And I spent a month just drawing graphs of absolute value functions in different contexts. I made an equation that used absolute values inside of absolute values inside of absolute values. That when you graphed it to find all the x and y that satisfy the equation, it was a picture of a chessboard. That turned me on. So that's just kind of an approach that I just really like. When I wrote volume 3 about sorting and searching, and I found that almost every important aspect of computer science somehow could be represented somehow in the context of searching and sorting. I was learning an awful lot of general techniques, even though I'm just studying a particular problem solution. So this morning I showed them satisfiability, and there's this beautiful theory of traces, which is quite exciting and important in lots of different parts of the field. So I look for the. But I always enjoy patterns the way you do when you're listening to music or seeing great pictures in a museum or something like that.
Question?
Over here.
Do you think there's a way to multiply matrices in quadratic type? Do you think there's a way to multiply matrices in quadratic type?
Do I think that the way to multiply matrices would you allow n squared log n?
Yeah, that's okay.
Okay, so one of the most classic questions of computational complexity is to find the exponent matrix multiplication and product calculus. So it surprised everybody when Volker Strauss in the late 60s was able to, instead of using n cubed, the steps which looked like he needed, he could do it at n to the 2.8 or something like the log base 2 of 7. And then more and more things happen. And I mentioned last hour that it's hard for me to it's hard for me to it's fixing the now you're going next to okay, so yeah, so when the second edition of Volume 2 came out, there were two things that were breaking news that I had to revise everything I'd written before. And one of them was that there was a brand new idea of studying the spectrum of Fourier transform in connection with studying random numbers that are produced. And so I had to several months adding completely new material. And the other part that was brand new when the second edition came out was about matrix multiplication. Because this exponent kept getting lower and lower by yet more fantastic technique. But then 1990s, one more technique was added to that arsenal, and for 20 years then the best known exponent nobody was able to find an improvement until last was I guess a year ago, year and a half ago, when my friend Virginia Williams figured out a way to lower the So she thinks that you might be able to get down to n squared. I spent a lot of time studying a paper by Jim Eve that he had written. Jim was a friend of mine from the University of Newcastle who was fighting cancer, but he spent 20 years of his life working on this problem, and at the end he thought he had found a way that would beam out the matrices in squared steps, and his friend asked me to look at his manuscript because he was too weak to continue writing it. And although I was working on other things, I wanted to do what I could for Jim, because nowadays, if you send a paper claiming to make its multiplication in square time, nobody has time to read it for some reason. Because this paper tend to be hard going. Anyway, so he had a very nice idea of using group theory of a certain kind, and I had high hopes for a while, but then it all broke down. In fact, the method that he had hoped would work, in fact, had a basic flaw. At that time, I came to a personal conclusion that I really doubted if we were ever going to get it n squared. But even if we do, I would imagine that the trade-off point would be only when n is much greater than the size of the universe. And so the question is really how fast can you multiply matrices and actually see the constant of proportionality is so astronomical that it's actually useful. So none of the methods that go beyond Straussen's is actually ever used in practice, as far as I know.
Okay.
Hello? To me it looks like solving a satisfiability problem is like wandering through that huge maze of possible solutions. And all those algorithms that I have seen yet tried to be a bit smarter than brute force and to find the shortcut through that maze. I think there's a big similarity to parsing. If you write a parser and you get an ambiguity in your grammar, the only solution is to look at all those paths and find out which path could match my grammar.
I'm sorry, I'm getting part of this, which I'm going through a large search space and then I'm getting lucky somehow. I don't understand that. I'm a little trouble hearing.
So try it again. I wanted to know from you if do you see the similarity in solving satisfiability problems to parsing? Because if you look at the
parsing, you say?
Yeah.
Okay. I think with parsing there was no phenomenon of something being 10 orders of magnitude faster than the other, as it happened with satisfiability. I showed you this example that with a very simple algorithm, you did 100 million steps, and with a improved algorithm, it was 2 trillion steps. And then, with this cloud learning method, we got it down to 250,000 steps. And when I say steps, these are references to memory. Each of these is, in one case you might say, this was a satisfiable problem, and so maybe these methods just stumbled on the solution, and so you're just lucky that the method did. So actually, I can tell you, but I did another test where number, but not into a 10-bit times a 10-bit, but I tried to factor it into a 9-bit times an 11-bit. I mean, this is a 20-bit number. Okay, so I said, so I set up the same thing, but instead of saying 10-10, I said 11-9. And that gave me another satisfactory problem, which turned out to be unsatisfiable. And so I tried all the solvers on that one, and the run times were comparable. It was 1 trillion times for the one that was so slow. It took 32 minutes while the others were doing it just like that. Again. So definitely something about that kind of satisfiability problem that makes it way harder on some than another. But when I was doing parsing, I was never, I would get some effects, but never more than quadratic or something. So it's one of the real fascinating things about combinatorial algorithms, that one idea can give you an incredible payoff. And in parsing, I never had that kind of feel.
This side?
Okay. It looks like that quantum computers could leave the state of experimental. And my question to you is, what do you think about quantum computers? Do they will change the way we think about programming and algorithms?
I got most of that, but what do I think about that?
Quantum computers.
I'm sorry. Quantum computers?
Yeah, sorry.
So, that's another very interesting question. And I think that I have absolutely no intuition for quantum computers. I think that there's something about the way my brain works that makes me very good at sequential computers and a little bit good at parallel computing. But when it comes to quantum computing, I'm totally at a loss. I read the papers and so on, but I know people, Scott Evans and so on, that really groove with this and understand it well. And my student form that I feel like Sergey Brin, who funded Google, was quite interesting. We were talking about quantum computers with Vaughan before he founded Google. But for me, it's a cold book. I just don't understand. I'll make a wild loop on quantum computers and things like this. And so if quantum computers come along, and it turns out that everybody starts using them, this will be good news for me in one sense, because then I can finish out of computer programming without I'm going to continue writing about sequential old-style non-quantum computers, which I understand, and nobody else will bother me by inventing new techniques.
Other questions?
Are you proud of the evolution of tech, since it's a de facto standard in computer science, at least for papers?
So this is something about tech.
Are you proud of the evolution?
Am I proud of tech?
Evolution of tech.
Evolution of tech. Well, I would say I'm happy that I see so many books that are beautiful that would not have been probably even been written without tech. So this makes me extremely happy. And so it's well, I guess I can tell the story. I told you last week again, but I was previous time I was in Linz was 1993, and I went from there to Prague. And I was waiting for a tram downtown Prague, and I looked into the schedule of when the tram comes, and it was time with tech. And also I visited a cathedral, and they had the time for the masses, and it was time with tech. And there was something distributed to the children. And it was done. So anyway, I was seeing the uses of tech there. But the problem was, there I am at the tram station, and it gives the schedule for Saturday, simple to and I didn't like the letter S. I said, oh no, I should have made that the middle stroke of the S a little thinner. There I was, I was inflicting my system on poor citizens in Prague. Because I hadn't designed it correctly. So the general idea is you have this thing where you say, boy, I'm really glad I influenced the world, but maybe I should have done better.
Why did you choose the title for your book, The Art of Computer Programming? Do you think computer programming is not?
Yeah, I think so. The word art, this question came up also long ago so it was the subject of the talk I gave when I won the Turing Award in the early 70s. And I joked at that time that I was thinking of a guy named Art Evans, and he was the art of computer programming. But more seriously, the word art in English is similar to Kunst in German, where it really, the historic meaning is that it means something that's different from nature, something that's influenced by human beings. So we have words like artificial and künstlich, I think. In other words, it means that it has something to do with human creativity and going beyond things that we can formalize. And while science, some people say, well, you say you're a computer scientist, but what about science? And why don't you call it the science of computer programming? But I think that it's nice that the more we learn, the more that we can formalize it. I like to say if we can explain it to a computer, then that kind of knowledge is science. But if we don't understand it well enough to explain it to a computer, it's art. It's something that people do in a magical way that we don't know. And then science advances because more of these things that we do with our art, we begin to understand and can formalize them and implement it in some way. So science is advancing, but then art advances too because the things we learned as we're doing that means that now we're able to do still more from it. And so art seems to keep ahead of science. But I'm thinking of art in that way as an aesthetic thing also. So creativity and also something that makes an object of art something that's satisfying and beautiful in some way.
My question would be, how do you see the relationship between mathematics and computer science?
How do I?
The relationship between mathematics and computer science.
In the context of the previous question, mathematics and computer science are the two kinds of knowledge that are not dependent on nature, but they're completely human-made. We get to, in mathematics and computer science, we get to make up the rules. We can define an operating system or a computer that has certain instructions, and we know what those instructions do. And but physicists have to try to decode the rules that are given in nature. And so the people in other sciences never really know that they've got an answer to anything. Mathematicians, computer scientists, we do. So first of all, there's this cut between all other sciences and the ones that are